Welcome to our meeting. I'm Sean Meehan, Chairman of the Society. Many of you know that already, but welcome to new members that are here for the first time or guests that are just coming to try it out. So tonight's talk is going to be about space rocks, rockets and robots by Professor Caroline Smith from the Natural History Museum. And I'll just go through the agenda very quickly. I'll do a very short introduction. And then the main presentation from Caroline, followed by some notices, a news item from Len Mann. By the way, Len is going to do it remotely from Cornwall. And we'll have the planetarium with Richard later on using the Stellarium program. Then the most important part, the refreshments at the end of the day. So just a quick word about Caroline. She has been here before, actually in 2012. And she talked to us about meteorites then, and it was a very interesting talk. I know it prompted a lot of people to go and explore that area of astronomy in more detail after the talk. So tonight, her talk is on space rocks, rockets, and robots. Basically, following on from the meteorites, you will see that there is great value in investigating the content of meteorites and collecting samples from other planets and so on. Caroline will explain all of that. Just a quick word about Caroline. I mentioned she's from the Natural History Museum. She's actually head of the collections of the science group looking after all the meteorite collection. And the meteorite collection at the Natural History Museum, if you don't already know, is one of the world's largest. It has over 2,000 pieces of meteorite and I think about 5,000 samples of various types and all. Caroline herself has won an award from ESA, the Aurora Award, for her work in that area. And she's also on several advisory committees, including the UK Space Agency and ESA. She has collaborated as well with NASA on proposed Mars exploration. So Caroline's speciality is the materials that are collected. She's also had an asteroid named after her, which is a nice accolade to have. So it's called asteroid 7635. And I don't think that's her telephone extension at the Natural History Museum, but it'd be interesting if it was. And it's called Caroline Smith, which is great. Her background is that she has a PhD from the Open University and also BSc Honours in Geology, which is our main focus there. So without any further ado, I'm going to hand you over to Caroline.
Thank you very much for that lovely welcome. It's very nice to be back and to see you all. I was just saying that actually I think this is the first public talk to an astronomical or a geological society that I've done since well before COVID. So it's really nice to be back and sort of see people in person and things like this. And also you are seeing the first use of a presentation of mine of our lovely new logo. Which has a nickname, but I won't tell you what the nickname is, but it's we think it looks a little bit like a coronavirus, but it isn't a coronavirus. So as Sean said, I'm going to be giving a presentation which does cover some aspects of meteorites, but also looking about how we use meteorites and how we link the work that we do on meteorites currently and what we've learned from meteorites to actually exploring wider in our solar system using the technology and the engineering skills of my colleagues at places like NASA and ESA and the UK Space Agency by looking at human and robotic exploration. So I'm going to cover sort of three main parts of the talk a little bit about meteorites. I'm not really going to talk so much today about sort of the classification of meteorites and the different types, but give you a background of how the study of meteorites actually started and how it's progressed over time. Then we'll sort of move into the age of rockets, into the space age, and then actually go into robotic exploration, which is something that I'm working a lot on at the moment, and using sort of robotic geologists, robotic explorers to explore these very far, these distant parts of our solar system that is very difficult, if not impossible, for humans to go and explore. So prior to the 1800s, there was very few known meteorites, and there were various reasons for this, which I'll go into. But within sort of the archaeological record and the historical records, we can see that there are uses and there are sort of literature references to meteorites being known to ancient peoples. So we know that Egyptians, in Egyptian culture, they used meteoritic iron in daggers and in beads and in other sort of high value ceremonial or high sort of treasure items. There's some very, very interesting work being done in Australia about the Aboriginal oral histories and how Aboriginal people in Australia would actually witness large fireballs and meteorite falls, and how those were actually recorded within the oral histories of these different tribes in Australia. Also in North America, there are two examples known in Canada and also in Arizona of meteorites basically being found and being used by the native tribes there, and again used often as sort of sacred objects or objects of importance. In Greenland, we've got evidence that the Inuits from Greenland also used iron as tools for cutting tools and other types of tools. They didn't have the technology to sort of smelt and produce iron, so they had to use native iron. It's very, very unusual to find native iron on the Earth's surface, but actually we've got iron tools made by the Inuits. And in fact, there's an image below, which is a lance, which is actually made of narwhal tusk. And you can see on the bottom, excuse me, I can't see where's the thing? There it is. You can see on the bottom, there's this small area of metal, and that is actually a piece of meteoritic iron. And then in Japan, we actually have the earliest witnessed and recovered meteorite fall in the Nagata meteorite. This fell in 861 AD. And the reason why this has actually was recovered and has been preserved is it happened to fall in the garden of a Shinto shrine. And the monks saw this as being a very important event, so decided to record it and save it as posterity. And that's probably the only reason why it is recorded, is actually where it fell in the garden of this Shinto shrine. So I mentioned about how in Australia, the Aboriginal histories often record celestial events, so comets, supernovae explosions and things. And this is a good example. This is one of 13 quite large craters in the Northern Territory near a place called Hembury. As I said, there's a sort of series of these craters from a large iron meteorite that fell and exploded and then sort of landed on the Earth in different bits. And there's actually, it's probably about 4,000 or 5,000 years ago this happened. And the actual local tribe there, the Aranda, actually have a name for this, which I won't say in the language because I'll probably muck it up, but it roughly translates to Sunwalk Fire Devil Rock. And the oral history is that this fire serpent came down. It was a sort of demonic serpent, hit the ground. This iron was produced, and still to this day there is a legend that if people drink water from the craters, you can see it's quite an arid area. It's a sort of semi-desert area, so water does collect in these craters, but people won't drink the water from the craters because they say that if you drink the water, you will turn into iron. Your insides will turn to iron. So that's quite clear that the ancestors must have seen this thing happen. Quite an amazing event to witness. And this tradition has been passed down through the oral histories. In archaeological evidence, we have actually a dagger that is made out of meteoritic metal, which was actually found in Tutankhamun's tomb. You can actually see it's there, just in the sarcophagus, and this is actually a color image of what the dagger looks like. And in fact, meteoritic iron is also represented in hieroglyphs from the same sort of period. So again, the Egyptians must have seen these things happening, seen these objects falling, realized there was something of importance. So we've got that historical record as well. Now, getting on to a more European context, the oldest meteorite that we have in Europe that was seen to fall and was subsequently recovered is this meteorite here. It's called Ensisheim. It's quite large. It's about that big. And this one fell in 1492. Now, again, very interesting context as to why this meteorite was actually retained. Yes, it was seen to fall, but it was actually preserved, was because Maximilian, who was the son of the Archduke Ferdinand, he was going off to have a battle with the French. Big sort of political turmoil within Europe at that time. And Maximilian was sort of going off with his army to battle the French, and this meteorite fell in the town of Ensisheim. Maximilian heard about it and he said, right, I want to go and have a look at this. And he spoke to his advisors, and the advisors said, oh, yes, this is obviously a sign from God that you are going to win the battle with the French. So Maximilian ordered that the meteorite, he spoke to the mayor of the town, and it was ordered and decreed that this meteorite be preserved within the town Maximilian subsequently did win the battle with the French, and therefore, obviously, this omen was true. I often wonder what would have happened if Maximilian had lost. We probably wouldn't have the meteorite recovered or retained. But this is the oldest witnessed fall that was recovered and retained in Europe. And there was a lot of publicity. Probably the first big publicity of a meteorite falling. A chap called Sebastian Brandt, who was a very sort of popular journalist at the time, would do these pamphlets that went all over that sort of part of Europe at the time. And this is actually an image of his pamphlet where he describes the actual falling of the meteorite. And there's this illustration, this woodcut here. And in fact, this pamphlet's written in German and in Latin. And interestingly, I speak neither German nor Latin, but apparently the translation is not a direct translation. There are subtle differences between the German and the Latin, which are believed to be a sort of their political, not political differences, but there's different political spins for the Latin speakers and to the native German speakers. And this is just an image to show you the lovely woodcut. So you can see this is Ensisheim. It's actually quite a sort of medieval fortress town. And the meteorite, it's quite interesting how the sort of drawing's done, because the meteorite here, this is a sort of woodcut or another version of it, so it's a bit clearer. I think it looks like the meteorite's actually going up into the clouds, but it's actually coming down. And it was witnessed by people who were around and about sort of in the fields at the time. And this is actually something that I'm going to refer to in a little bit. In fact, now. So we jump forward about 300 years to this chap here. This is Ernst Chladni. He was a very, very interesting man. You can do a lot of research on him. A real polymath, born to quite a sort of well-to-do Austrian family. And he really was an amazing musician and a linguist. And a physicist and a mathematician. And he really wanted to study music or science. That's really what he wanted to do. But weirdly, science was not seen as a particularly good profession, and music was certainly not seen as a good profession for somebody of his standing. So he was sort of forced to do legal training and go into the law. But he actually was a very, very good musician and very, very good a mathematician and physicist. And he's actually very famous for looking at harmonics and something called Chladni figures. So you can look him up, very interesting man. And he got quite interested in meteorites and these accounts of people seeing these objects fall from the sky. And he wrote to people and wrote to sort of groups and sort of, because he was very well connected because of his status. And he actually sort of said, well, hang on. He said, I'm reading sort of semi-contemporaneous reports of people seeing stones and bits of metal falling from the sky. And I'm also reading historical reports. And everybody is reporting the same phenomenon. Because at the time, the scientific sort of elite thought that meteorites, basically, they couldn't really be real things falling from the sky. It must be these peasants who are working the fields and seeing these things fall. They must just be imagining it or making it up. And Chladni's legal training was like, well, hang on. How are all these people who are in different countries and at different times reporting the same phenomena? There must be something in this. So he actually wrote, this is known as the sort of, or regarded as the first sort of serious scientific study on meteorites. In 1794, it was published, and you can see there, it's called On the Origin of the Mass of Iron Found by Pallas. So this was Pallas in exploration in Russia earlier in the 1700s, and of other similar iron masses, and on a few natural phenomena connected therewith. And Chladni was, again, an amazing book he wrote. He recorded a lot of these eyewitness reports. He recorded the physical and chemical properties of the materials that he was able to study. And he came up with a number of conclusions. So these are the main conclusions that he came up with, that masses of stone and iron do indeed fall from the sky, that the fireballs that are witnessed form from frictional heating during deceleration of these bodies as they fall through the atmosphere, that these solid bodies are unrelated to the Earth or the Sun. And that was a very important point, because the few scientists who said, well, maybe there is something in this, they said, oh, that's probably maybe volcanic rocks that have been blasted out into the atmosphere and then have fallen back down a long time later, or possibly from the moon. And at that point, the Earth and the Moon were considered almost to be one thing. They were considered to be the same system. So Chladni's observation that these are unrelated to the Earth or the Sun or the Moon was a very, very important observation, and that these bodies originate in cosmic space. So outside the Earth-Moon system, either as small bodies that never accumulated into planets, fragments of planets that were disrupted by explosions, or fragments of planets that were disrupted by collisions. I've just realized I forgot to put my timer on. So somebody's going to have to give me a nod in about 15, 20 minutes. So 1794, remember, nobody was studying meteorites. People didn't think they were worth studying. And Chladni got that one right. He got that one wrong, but he got that one right. So quite amazingly, he really did hit the nail on the head with most of his conclusions from that book he wrote in 1794. Now, we jump forward a year. These are some pictures of the Wold Cottage meteorites. This is the first meteorite to fall in the UK and be recovered and preserved. So this meteorite fell in 1795 up in Yorkshire. It fell near the sort of, it's like a hamlet, a place called Wold Cottage. It's quite close to a place called Wold Newton. And this was a very interesting story. There was a young man called John Shipley. He was a sort of ploughboy, and there was a big bang, big explosion. And then shortly after, he was nearly hit by this meteorite that landed about 2 meters from him, and it covered him with mud and sort of debris. Now, there was a chap called Edward Topham who lived very close by. Edward Topham was very sort of well connected in the London sort of coffee houses and London society, and he realized there was a great bit of sort of excitement and not propaganda, but he could do a nice bit of publicity about this. So Topham wrote about this meteorite and about the things that people had witnessed and had heard, and he actually had the meteorite, and it was displayed down in the coffee houses all around Piccadilly. He also erected this monument, which until relatively recently was the first and only monument to a meteorite falling anywhere in the world, although there are some more now, but this was the first one ever put up to celebrate the fall of a meteorite. And Sowerby, James Sowerby, who was a very famous mineralogist and natural historian, he studied the Wold Cottage meteorite, and you can see there's a painting of him here, and there you can see there's the meteorite in the background. So this was the sort of first in the UK. There had been some other falls in France around the same time, and this was beginning to pique the interest of the scientific elite. So we move on just a few years later. This is an image on the left of some famous scientists. The chap here in the foreground is William Smith, who's often known as the father of geology. He produced the first geological maps ever to be made. This chap here is Edward Howard, who was a very talented young chemist. And this is William Allen, who was also another very good chemist. And Howard was quite interested in the chemical composition of these weird things that had been said to fall from space. And he was actually tasked by, and the name has just gone out of my head, who was the president of the Royal Society at the time. He was very famous. How embarrassing. Famous president of the Royal Society, it'll probably come to me in about 10 minutes, tasked Howard with actually doing some research on these objects and presenting a paper at the Royal Society, which Howard actually did in 1802. And this is a scan of his paper, and the title of the paper is Experiments and Observations on Certain Stony and Metalline Substances which at different times have fallen on the Earth. And I have actually put there in the brackets are said to, because you might be able to see there's actually some annotation here. And the president of the Royal Society, Joseph Banks, there we go. So Joseph Banks said to Howard, you know, it's still not certain that these things have fallen on the Earth from the sky. I'm not happy with you saying that. I'm going to say are said to have fallen from. So that was actually Banks that was still being a little bit hesitant, even though Howard in his paper said these things have got chemistries and minerals in them that are nothing like those on Earth. They have to be from somewhere else. So it was really in the early 1800s to sort of 1820s, 1830s, that people, the scientific elite at the time and the scientists really only started to sort of accept-ish that meteorites actually were interesting things and they were from space. They were not of the Earth-Moon system. And this is a great introduction to the Catalogue of Meteorites, which is a publication that the Natural History Museum has been doing since the about the mid-1800s, actually. And I just love this bit here. It says, until nearly 50 years after the establishment of the British Museum, that was 1753, meteorite collections nowhere existed, for the reports of the fall of stones from the sky were then treated as absurd, and the exhibition of such stones in a public museum would have been a matter for ridicule. So it just goes to show you how in that sort of period of time, over about 50 years, from the sort of mid-latish 1700s up to the sort of mid-early 19th century, meteorites were basically not seen as worthy of scientific study by anyone who had any chops, which is one of the reasons why we don't have many meteorites in the collections pre about 1800. Lots of meteorites would have fallen in Europe and the rest of the world. We just don't have them actually retained and preserved. So I will go from the sort of early 1800s and the birth of meteoritics. So this is a video. Hopefully it will work. So it's a bit pixelated, I'm afraid, but that is a fantastic fireball from the 28th of February 2021. And this is the famous Winchcombe meteorite, which some of you may have heard of. So this is the most recent meteorite to fall on the UK and be recovered. There have been at least 2 more since Winchcombe. Unfortunately, we haven't been able to find them. But we were able to get out very quickly, even though it was during COVID. I unfortunately could not go out in the field to help go and find pieces, because I was at the museum getting all the letters done to do authorizations to travel. So I was doing all of the admin back at the ranch. But there was a large team. We're able to go out to Winchcombe, which is in Gloucestershire, and collect a number of fragments of the Winchcombe meteorite. And as soon as the team got out there, they realized this was something very, very special. It was a very unusual type of meteorite. So you can see this splat on the driveway. That's probably the most famous piece. That's actually was the largest piece. You can see it's in small fragments now. This fell on Rob and Catherine Wilcox Drive. They were canny enough to work out that something had gone on, and they contacted the Open University and us to let us know that they thought this meteorite had fallen in their driveway. And they've been absolutely wonderful. They've been great advocates and partners with us to work on this meteorite. But you can see the pieces, they're very dark. They almost look like a sort of charcoal briquette. This is a piece, in the museum, one of the pieces that we have in the collection. You can see it's this very, very dark black color with sort of white bits in. And it turns out that this is, not only is this the first meteorite to fall and be recovered in the UK for 30 years, it's also the first meteorite of a type called a carbonaceous chondrite. And carbonaceous chondrites are really interesting because they are some of the we call them the most primitive meteorites that we have. So since they formed early in our solar system about 4.5 billion years ago, they have undergone very little changes. They sort of retain those very primitive characteristics. They're also very interesting because they contain a lot of organic carbon and they contain a lot of water. And that's very interesting when you start thinking about the ingredients for life to arrive on Earth. Where did that come from? Well, you've got those ingredients you need in meteorites like the carbonaceous chondrites. And because there was a lot of footage of this meteorite falling, the fireball taken from different angles on people's doorbell cams, on some of the UK fireball network cameras, a very accurate orbit was able to be determined for this meteorite. So this is just an image taken from the paper in Science Advances that we published. And you can see the different orbits. All of these orbits here are of different carbonaceous chondrites that have fallen recently and that we've been able to determine the orbits from. And you can see here Winchcombe sort of in that same sort of area. So very outer bit of the asteroid belt, actually relatively close to the orbit of Jupiter. So these are outer asteroid belt materials. And as I said, really interesting to study because they retain those primitive characteristics of the very early solar system. So we'll go on, oops. So hopefully this video will play. Why is my video not playing? Maybe I need to do this. Oh dear. There we go. So So why do you think I'm showing a picture of the Trinity atomic, or video of the Trinity atomic bomb? Any ideas? Sort of. Sorry, what was the other one? Some of the elements in it, sort of, but not quite. So we don't really get not the right type of elements, but the technology that was developed to actually make the first atomic weapons has a direct link to the type of work that we do now. So here are two fathers of what we call cosmochemistry, so the field of looking at chemicals and chemistry of things like meteorites. So we've got Alfred Near there and Ernest Lawrence, so two very, very famous physicists and chemical physicists. They worked within the Manhattan program, which was obviously the American program with involvement from the UK and Canada as well, to actually develop the first two atomic weapons. And one of the things that was developed was this thing called a calytron. What it is, it's huge. These are absolutely massive. This thing is literally about the size of a sort of football field. And this is a very big mass spectrometer, a big sort of particle accelerator mass spectrometer. And this was developed to try and separate uranium from the uranium isotopes that are not particularly useful for atomic weapons, and actually collect and refine the isotopes that are very useful for nuclear weapons because they'll fission. So this is a massive thing, but actually being able to separate elements into different types of isotopes and then be able to collect those, or if you wanted to measure them, has a direct link to the types of chemistry and the types of analysis that we're doing today in the lab. So as I said, this calytron here in the K-12 plant, which was in Oak Ridge in Tennessee, developing that uranium for the first atomic bombs, actually links directly to instruments like this, which now take up half a lab, or in some cases even a bench in the lab, to look at the chemistry in very, very fine detail of the meteorites. So very tiny, tiny, tiny amounts of different types of elements, but also crucially the different isotopes of those elements, because that can tell us a huge amount of information about when that meteorite formed and the different components formed, where it formed, and what subsequently happened to it. So this is just an image here. This is a meteorite called Allende. It's another type of carbonaceous chondrite. So these very interesting ones if you're interested in working out how the solar system formed and then subsequently evolved. And this is actually an electron image. This is a scanning electron image. What we've done is we've false colored it because you can actually see, you can actually work out what the elemental composition here. So in this image, white and yellow and blue are elements like calcium and aluminium. Green is magnesium and red is iron. And you can see here very clearly there's this massive lump here. This is a very naughty photo. Why is this a naughty photo? There's no scale bar on it. Tut, tut, tut. I shall have to rectify that. But this I can tell you is actually probably probably about 500-600. It's probably about 5 or 6 millimeters across, sorry. So as I say, microns. So quite large. And you can see it's all white and yellow and blue. There's a whitey yellowy thing here. There's another one there. There's one there. If you get your eye, you'll see a few. There's a very small blue thing down there. These are these things called calcium aluminium rich inclusions. And we can actually use mass spectrometry techniques to work out the abundance of different isotopes of elements like uranium, like lead, like potassium, like argon, rubidium, strontium, lots of different elements that we can use as geological clocks. So these call them geochronometers to actually work out when these objects formed. And when we date these CAIs, as we call them, these calcium aluminium rich inclusions, they come out with these very old ages of 4,567 million years, so 4.6 billion, 4,566, so very, very old ages. And these are the oldest things, or some of the oldest things that we can actually date in meteorites. And this is what gives this sort of clock to say the solar system is 4.5 billion years old. And as I said, there is a direct pathway, there's a direct technological and analytical pathway back to the development of the atomic bomb, to provide those technical and analytical advances for us to now be able to date these amazing samples. And being able to date those amazing samples actually gives us an idea, and looking at their textures, looking at some of the other properties that they have, and comparing these with what our friends who are astronomers can see using amazing telescopes like the James Webb, actually gives us this really good understanding of what our solar system was like just when it was beginning to form. So you have this wonderful protoplanetary disk with the young sun in the middle, this swirling disk of gas and dust. And as some of that gas starts to condense from these very, very high temperatures, you get CAIs forming, you get other things called chondrules forming, they're very old as well. And you get this amazing, turbulent, dusty, gassy disk that eventually agglomerates and cools down, and that's how you actually get our planets forming. So using CAIs and comparing with what we actually see today using astronomical observations can give us that window back in time to 4.5 billion years when our solar system was just beginning to form. Oh, don't need to see that again. So we're going to jump ahead now. So this is a lovely image. I was going to include a video, but actually the videos I could find weren't actually that good. But this is a lovely image of the launch of Apollo 11, which was the first Apollo mission of the 6 that did actually land on the moon in July 1969. And so, you know, why is that relevant? Well, it's relevant because this, you know, one of the main mission objectives of the Apollo mission, yes, it was political, yes, it was about technology, but it was also absolutely scientific about where is the moon from, how did the moon form. There were various suggestions about how our moon formed, and you know, we said we're only going to know if we actually have pieces of moon rock, and we need to send people there to go and get them. So we had this series of Apollo missions, and in fact, the Apollo astronauts returned just under 400 kilograms of moon rocks, and those are still being studied today, and there are still amazing discoveries being made on those samples 50 plus years after the first ones returned. So if I just play this. So this is actually the return of the Apollo 11 capsule. So there's the capsule upside down. Now, what I find interesting about this, it relates to the next bit of the talk. There's the Navy diver going in, somebody filming. And you can see that they're wearing, these are the astronauts, you can see that they're wearing these coveralls, these sorts of...
This historic mission. Some way, when those two Americans stepped on the moon,
you see he's got like a sort of breathing apparatus on.
Together. That it is that spirit, the spirit of Apollo, that America can now help to bring to our relations with other nations.
So the reason why the astronauts were wearing those grey sort of oversuits with breathing things, it was because at that time there was no certainty if there was. So I'll go back. We were not sure. The scientists were not sure whether the moon surface and the rocks on the moon could potentially contain something that was hazardous to Earth's biosphere. And it was only when the Apollo missions actually really got going that the international organizations and the international scientific community said, what happens if we go to the moon or indeed somewhere else and we bring back stuff that is dangerous to Earth's biosphere? So as well as doing the science of actually how the moon formed and all the cool stuff like that, the Apollo missions actually set off something which is a big part of science, and it's something that I work in, called planetary protection. And I'll just show you the next video. And there's a bit in this that really makes me chuckle.
To protect against any possible lunar contamination, the astronauts put on airtight special garments before coming aboard the rescue ship. They transferred directly from the helicopter to a mobile quarantine van, in which they would be flown back to the Manned Spacecraft Center in Houston, Texas.
So there's a couple of things that I find very interesting about watching this. So do you remember the first video I showed where the Navy diver comes out? So the inside of that Apollo capsule is absolutely riddled with moon dust. it lands on the sea and they open the door so dust can come out, and the diver goes up, throws the suits in, they put the suits on in the capsule, and then so there's all stuff on the suits. So that's not very good. But at the time they didn't think about it. And then I'll just show this video again. Unfortunately, I've not been able to find a video or a version of this that shows it, but I just want to point out this chap.
To protect against any possible lunar contamination, the astronauts put on airtight special garments before coming aboard.
And see that thing there? That looks like a fire extinguisher. Well, I've seen another version of this where, as the astronauts go along, that's got a load of bleach in, and he's going along bleaching the floor after the astronauts have walked on it.
They transferred.
So it was, you know, they were doing the best they could at the time,
in which they would be flown
but
back
with
to the manned
2020 hindsight,
in Houston,
not
Texas.
so good. Now, obviously, we soon realized that there was nothing hazardous about rocks collected from the moon, and these quarantine procedures were actually finished, I think, in Apollo 14 was the first mission where they didn't follow these rigorous, in inverted commas, quarantine procedures. And there you go. That's just an image of the astronauts in the this sort of command quarantine thing, and that was literally airlifted. The whole thing was put in an aircraft into Houston, and they went into the Manned Space Flight Center, into the Lunar Receiving Laboratory, into the quarantine section, and they stayed in there. I think it was for 2 or 3 weeks until it was decided that they didn't have any lunar death bugs on them. But as I mentioned, the sort of development of the Apollo missions did get the scientific establishment around the world thinking, oh, well, what if there's something dangerous on the moon? So in fact, the United Nations drew up the Outer Space Treaty in 1967, and Article 9 specifically discusses this issue of potentially contaminating the Earth with stuff returned from space missions, or indeed potentially contaminating other places that we would go and visit on our exploration missions. And the key part is that bit, which I won't read out because it's covered in the next slide. So the wording talks about the moon and other celestial bodies and conduct exploration of them so as to avoid their harmful contamination. That's what we call forward contamination. So we don't want to take anything hitchhikers on any of our space missions that are landing on Mars or the moon or Titan or anywhere else that could potentially contaminate those places and cause damage to those places. That's what we call forward contamination. And similarly, if we're bringing material back with us to study in labs on Earth, we don't want to contaminate the Earth with any Martian death bugs that kills all the bees or kills everyone. That's called backward contamination. And both of these, forward and backward contamination, are taken very, very seriously by all of the spacefaring nations. And there, as I said, there's international treaties. This is taken extremely, extremely seriously. So we have this thing. We want to avoid this at all costs. It came from outer space. NASA has a planetary protection office that's staffed by expert scientists from biological, chemical and engineering backgrounds. ESA also has planetary protection officers, as I said, taken very, very seriously. So seriously that if there is a mission that has planetary protection requirements in it and that planetary protection officer is not happy, for example, with how a spacecraft has been sterilized before it launches to somewhere like Mars, they can say that is not going. They can literally say that mission is not launching, you know, multi-billion-dollar missions. So very, very important people doing a very, very important job, because we all want to avoid the whole it came from outer space. There is a really good book. If you've not read this book, I really would recommend it. So this is Michael Crichton, who's also famous for writing the Jurassic Park books. This was his first book. It was an international bestseller, and really made his name. And he actually based this book on a lot of the history and what had been done for the the preparation for the Apollo missions. You see, the book came out in 1969, the same year as Apollo 11 launched and returned. And I'll just tell you a little anecdote. My dad actually had this. This is the same copy that my dad had. Apparently, he picked it up. He used to work for Pan Am, and he picked it up in an airport and read it on the plane. And I read it when I was about, first read it when I was about 12 or 13. And I remember thinking, wow, that's really cool. I couldn't believe that I'm actually doing that sort of work now. It just shows you how sort of fate goes on. But there's various bits, there's been various versions of the book made into films and TV programs. They're all absolutely rubbish apart from the original one. And if you do put this on YouTube, I could get in trouble because this is actually nicked off YouTube. And it's a universal, so maybe delete this bit or just, but I just love this. And it's actually weirdly accurate.
A special laboratory in Nevada. We brought you here. You're sick.
In a true biological crisis, which our exploration of space could bring about, the present lunar receiving laboratory might prove inadequate. I therefore urge the establishment of a facility to deal specifically with an extraterrestrial form of life.
Seems to me, General, Dr. Stone put one over on it. In fact, he made us all think his wildfire lab could handle any contamination from outer space.
Isolate and identify.
To no accident. I suspect they were looking for the ultimate biological weapon.
That bit's not accurate.
It's crazy. I didn't know buzzards fly at night.
Buzzards only come when something's dead.
Landau Decker to Cable 1. What's that?
We see bodies. Lots of them.
These people were cut down in mid-stride.
Everybody's dead. No, did it.
We recommend calling a wildfire alert. All members of your team have been cleared and are now being called in.
If things get out of control, even you can't work miracles.
There's a car and they got guns. What's going on? This communication is being monitored. Never believe this could really happen. You still, you know it.
Make it possible.
I wish I could believe it.
Whether you do or not, the only important thing now is to find the antidote.
Even with the microscope that line.
I'm turning off the oxygen. Experiment with your own life, damn it.
Now, it really is a very, very good book. And in many ways, it's actually very accurate in terms of some of the things that are described and the measures that were sort of implemented and thought to be implemented back in the sort of mid to late 1960s when this work was being developed. But just to sort of reiterate, you know, it's something that is taken extremely seriously, and it's being taken extremely seriously, especially because we are in a period of enhanced exploration of the planet Mars. And you would say, well, why would you be more concerned about Mars or something like that? Well, the reason is that we are interested in Mars is because it's one of the places within our solar system that there is increasing geological evidence that Mars may well have harbored life back in its distant past. It may not be alive today, or indeed it may be alive today, depending on your point of view. And there's a lot of debate within science about whether there is actually still life. And I don't mean little green men, I mean very simple microbial life, still extant, still living on Mars. And that's one of the big drivers actually for the exploration programs of NASA and ESA and other spacefaring nations who are going to Mars and sending satellites and sending landing missions to increase our knowledge of the red planet. And you can see here, this is actually a slide I nicked from my colleagues at NASA. And they have this strategy about follow the water. So we've now got conclusive evidence that liquid water certainly did exist on Mars in the past. And there's very strong signs to say that you could also get liquid water and water just below the surface of Mars in certain different places. So it's a very, very interesting place to go to scientifically, but also as well in terms of extended human exploration. We're hopefully going to be going back to the moon in the next couple of years with NASA Artemis's mission, and that is a stepping stone for then human exploration out further into the solar system, including to Mars. So NASA launched a mission in July 2020, the Mars 2020 mission, and it arrived in February of 21. So it took about 7 months, 7-8 months to get to Mars. And the mission is still in operation, and it's currently on Sol, which is a Mars day, 982 days of operations, and it's working extremely well. And we're really pleased how it's going. It is one of the most complicated rovers ever to be sent to Mars. It's got an absolutely fantastic wealth of scientific payload. It really is a fantastic robot geologist. You can see the different payload on there, the different scientific instruments. I'm not going to tell you about each one, but this is the one that I'm most interested in here, Sherlock, which is an instrument to be able to look for the signs of organic molecules present in the rocks. And that is an instrument that I'm actually on the science team for. So that's really good fun, although late nights on a Tuesday because we work on American time. But really interesting results and really fantastic international team working on that instrument. So here is this is again taken from today. The rover is actually having a bit of a holiday because Mars is in conjunction, and my friends who actually drive the rover and send the commands up, they're all having a bit of a break as well. And of course, it was Thanksgiving yesterday in the US, so they're having a nice break. So the rover's actually traveled nearly 14 miles since it landed in February 2021, landed around here in the Jezero crater region, and it's been going around, driving around, and it's up here now in what we call the Delta region, collecting rock samples to actually be able to study those samples on Earth. And this is a really important part of the rover's job. Not only is the rover there to do the in situ analyses and take the photographs and look and do the analyses of the rocks that it's seeing actually on the surface of Mars, it's also designed to actually collect samples of those interesting rocks with hopefully a return to Earth in about 10 years time, although it seems to be about 10 years time for about the last however many years. So it's a really fantastic mission, as I said. It's doing a lot of really cool science. It's already telling us much more about the surface of Mars, and as particularly that region, the Jezero crater. It's got a fantastic technology demonstrator. I'll just go back one slide. So you can see there's a little picture here of that's the little Mars copter Ingenuity, which is the first helicopter to fly not on the surface of the Earth. And I will be quite honest with you, I didn't think it was going to work. It has worked, and it's worked extremely well, much better than expected. So also technology demonstrating on this mission. And as I said, the first step in the Mars sample return program to actually bring samples of Mars back to Earth, where we know exactly their geological context. We know exactly where they came from on Mars, what type of rock, and then we can study those on Earth, just as we would do if we were geologists in doing exploration on Earth. You'd go and have a look, you'd find some interesting samples, and you'd bring them back to your labs to study. So people say, well, why do you need to do that? You know, you've got Martian meteorites. They're great. I love studying Martian meteorites. We've got images of Mars, we've got the rovers. Why do you need to bring the stuff back? Well, the reason is because we will only be able to do those definitive studies to say, yes, there is evidence of fossil life in these samples, or yes, there is even evidence of alive life in these samples, by using the full weight of the analytical instrumentation that we've got on Earth that we cannot miniaturize to put onto a rover. So things like a transmission electron microscope, X-ray microtomography, scanning electron microscopes, big mass spectrometers, synchrotron facilities. This is the Diamond Light Source in Harwell in Oxfordshire. Something, you know, that is a large building next to a very large thing. You cannot shrink that down to stick it on a rover. But these are the types of equipment that you need to be able to make those massive discoveries of, was there ever life on Mars? Is even life going on there today? So that's why we have to bring these samples back. Now, I mentioned there is concern about whether if there is life in there, or indeed anything else in there that could cause damage to Earth's biosphere. This is taken extraordinarily seriously by all of the agencies, and this is just a snapshot of some of the publications that have been done in the last 20 years or so, planning for actually bringing samples back from Mars. So there's a huge effort going on, massive groups, multinational groups with diverse expertise, really thinking about this to make sure that we can bring the samples back safely. They're not going to do any harm to Earth or with the scientists working on them, and we can do some really fun science. And talking of fun science, so again, so quite hot off the press, you may have seen about this mission quite recently. This is the OSIRIS-REx mission. This is an asteroid sample return mission by NASA. So a mission to go and land on an asteroid, pick up some bits and bring it back to Earth. You can see it was a 7-year mission. I was very lucky. I actually went to go and see this mission launch at Cape Canaveral in 2016, and the capsule successfully returned to Earth just a couple of months ago at the end of September. This is an image of the asteroid, not the asteroid, it's an image of the spacecraft. You can see it's got a number of different payload on it. These are different imaging systems to actually look at the texture of the asteroid, its physical properties on the surface, but also its mineralogical and chemical properties. This is a laser altimeter provided by the Canadian Space Agency. But this is the thing that most interests us. This is something called the TAG-SAM. It's called the touch and go sampler. And this was the device that actually collected sample of the surface of the asteroid to return to Earth. And this is a nice GIF of the asteroid Bennu. You can see it's got this sort of quite interesting shape. And there were 4 areas shortlisted to actually be okay to go and land. So there was 2 considerations. They wanted an area that looked scientifically interesting and that would get good samples from a scientific perspective, but also as well as engineering considerations. You can't go and land like on a massive boulder or near a massive boulder because the spacecraft might get damaged. So a lot of conversation between the scientists and the engineers, and these 4 areas were shortlisted, and then subsequently it was the Nightingale area that was chosen for the sampling. And this is actually just a little animated GIF of the actual sampling taking place. The images are a bit grainy. This is actually the spacecraft taking the image of it sampling the surface of the asteroid. So quite amazing. All of this stuff, that's all debris that was sort of kicked up. So the way that the touch and go sampler works is it touches and it actually blows out nitrogen, which dislodges pieces, and then they sort of go up into the mechanism. So quite a clever piece of technology. Anyway, it worked very well. The mission requirement was to collect 60 grams of sample in total. This is the actual sample capsule landing back at the Utah Test and Training Range at the end of September. This is 3 people I know. That's Scott Sanford. This is one of my best friends, Francis, who's head of curation at NASA, and Dante Loretta, who's the principal investigator of the mission. And so this is the sample return capsule, and the sample is safely, the TAG-SAM, the sampling head is safely wrapped up in there, being protected from the environment of the Earth, because these are very important samples. We don't want them getting contaminated by Earth stuff at all. Sample was taken back, rushed back to the Johnson Space Center in Houston, where the curatorial team put it into a very sophisticated glove box under very controlled conditions to start opening the container and seeing what was inside. That's my friend Rachel there, and that's my friend Nicole there. So they were working very, very hard, and that's what they've done here is they've actually just lifted the lid off the inner part of the sample container. So nowhere actually near the physical sample. This is like the outer edges. And hopefully you can see in here, can you see there's all black stuff? That's bits of dust. So they were very excited when they saw that. So this is a bit of a clearer picture. So the TAG-SAM head and the actual main sample container bit is right in here. But hopefully you can see, so on the top, it's a bit dirty, and all around here, see all this black dust. That sample that has actually come out of the sample container because it was full, although it's been retained within the wider mechanism. And this is really, really cool stuff. This is the first samples that were able to be accessed. And in fact, they've announced that they haven't even gone into where the main sample is, and they've already recovered 76 grams of material. Bearing in mind the mission said bring back 60. So they've already got 76 grams. They've not even got into the good stuff yet. So this material is being worked on by scientists around the world, including colleagues at the Natural History Museum. We've got some. I had a look at it the other day. Just looks like little black pieces, but it's very, very exciting. And this is, again, being used to work out really, what is this stuff made of? This is the stuff that our solar system formed from, and is really the building blocks of our planet and the rest of the solar system. And this is just another image there. So again, this is not even in the main bit of the sample containment system. This is the outside, and you can see all of this stuff here. I mean, it's really quite incredible. It's a real bonanza for us. So very, very exciting. So I've whiffled on enough. So hopefully I've given you a bit of a whirlwind tour right back to the sort of dawn of the study of meteorites as scientifically interesting objects through the sort of space age, in the sort of 50s and 60s and 70s, and then on to obviously the work that we're currently doing and what we're aspiring to in things like Mars sample return. But one of the things that I would really like to just finish on actually is that last bit there, is that, you know, the UK has and is a leader in this type of research. And this is one of the things that it's a really, you know, that it's been, sometimes it's not been so good, but, you know, we have had investment from the government and other funding agencies, and it's really beginning to reap its rewards. So, you know, as I said, we have people from the museum, not me because I'm busy doing other things, but some of my colleagues, they're in that preliminary examination team for the OSIRIS-REx mission. The reason we were asked to be involved with that, because we are world leaders in our field. I'm working with NASA and ESA on the Mars sample return stuff. The reason why we're doing that is because they couldn't find anyone else to do it. But there's, you know, it's a really, really good thing that we're doing. And I think that, you know, we should all be very proud that the UK, despite not a huge amount of investment, but some investment, we punch well above our weight, and we're seen as excellent partners in these massive international endeavours to really explore our solar system and better understand how we got here and where we're going in the future. Anyway, that's it. I'm happy to take questions. I hope that was interesting. It was a bit of a sort of, all, you know, it was a bit, what's the word? Jumped around a bit, but hopefully you could see a sort of thread. Anyway, thank you very much.
Yeah, thank you very much for that indeed. I am very conscious that Caroline needs to get away quite sharply, so we'll limit it to maybe 2 or 3 questions. Has anybody got a question? If you do, I'll come down with the microphone so that the people on Zoom can hear it. So raise your hand if you've got a question.
Does when the meteorites come back into the atmosphere and they re-enter and get hot, does it change the structure of them in some way?
No, it doesn't. Not as far as we can tell. So what happens is, as they come through the atmosphere, because they're going so quickly, the outer surface ablates, and in fact, so the outer surface just melts maybe a few millimeters, and it gets blasted off as it's, you know, it sort of gets blown off, and so you actually don't get the heat sort of propagating enough into the actual meteorite itself, which is actually quite good, because if it did, as you said, it could completely change its sort of characteristics. It could also actually cause things. There is some evidence that you might actually get water and ice potentially in some freshly fallen meteorites. So again, that water and ice could actually be obviously melted if the heat from the coming through the atmosphere propagated through. What we do with in fact, I'm just going to whiz back. But the picture of Winchcombe I showed you, I don't know if you saw on the left-hand image, it was quite black, and then there was a little patch of sort of browny surface. So that's actually the what we call the fusion crust. That's that burnt outside layer. And bit here, can you see that little patch in the middle? So that's actually the fusion crust of that bit of Winchcombe, and that is only about 1 millimeter thick. And we can actually, people have actually studied, so, okay, when you go to the fusion crust and you go in, how far down is it from fusion crust sort of starting and fusion crust stopping and, you know, real inside meteorite? And it's usually 1 millimeter or 2, no more than that. But one of the things we do when we sample meteorites to send out to scientists, unless they ask us to say, please include some fusion crust, we always go a bit deeper in to avoid not only any potential changes from that meteorite coming through the atmosphere, but also any changes of it hanging around in the museum. So it's to try and avoid that contamination.
We got a question from the chat, so I'm going to hand over to Andrew for that.
Yep. So yeah, Len says, yeah, great talk. He has a question. You say there are strong indications that there was or is life on Mars, and he just wondered if you could perhaps expand on that at all, please.
Okay, so we are seeing there is increasing evidence that early in Mars's history, in the first about 500 million years or so of Mars's history, that it had the geological conditions, the environment were right for life to start. And indeed were much more conducive for life to sort of start and develop than the early Earth was. So we assume that early Mars and early Earth were bombarded with meteorites and cosmic dust containing those ingredients you need for life, so organic molecules. And in fact, in meteorites, like the carbonaceous chondrites, we find all of the amino acids you need to make RNA and DNA. So you've got those chemical ingredients landing on those places. And in the case of Mars, it was a much more habitable environment early in its history. It was cooler than the Earth. It had liquid water before the early Earth did. So there was a lot of sort of circumstantial evidence, let's say, that if life had arisen on Mars, if life was going to arise somewhere early in the solar system, Mars would be a great place for life to arise and potentially last for a few hundred millions of years. Now, we haven't found there's no direct evidence. We haven't found the little microbes or the little fossil microbes yet, but that's one of the aims of the Mars Perseverance mission, and collecting those sample tubes is actually to say, right, can we find that microscopic evidence? They're called biosignatures, that microscopic and microchemical evidence of fossilized early life on Mars. And there is compelling evidence to say that, yes, we might do, which is why we want to bring those samples back and have a look. So that's past life on Mars. Now, present life on Mars is a little bit more controversial, let's say. So we know that Mars lost its atmosphere. Mars has been a very inhospitable place for life. It's very cold, it's very dry. It's bombarded. It doesn't have a protective atmosphere, so it's bombarded by ultraviolet light and galactic cosmic rays from space. However, below the surface of Mars, it is much more hospitable. So we can see from various types of analyses that there is almost certainly ice below the surface of Mars in places, and in some places possibly even pockets of liquid water below the surface of Mars. We know that water is a critical ingredient for life. We also know that life finds a way. So the suggestion is that if life did arise on Mars and was beginning to sort of do lifey things, was beginning to thrive, as the environment changed and it got more inhospitable, that life would try and change how it lived. So maybe it would start burrowing down, sort of these microbes going down further below the surface of the Mars to find these sort of protected niche habitats where they could survive. And that is one of the reasons why ESA's Rosalind Franklin rover, which is due to launch in 2028, fingers crossed, has a drill that can actually drill down 2 meters into the surface of Mars. The idea being that that gets to the sort of depths where, if there is extant life, that is where we will find it. We're not going to find it on the surface. It's too inhospitable. But if it's there, it's going to be living below the surface. But I stress, we are not talking about the Anunnaki or Greys or anything like that. I do like Ancient Aliens, I have to say, but for comedy purposes, it's not that sort of life. We are going to be talking sort of simple microbial type life. Does that answer your question?
Thank you. Yeah, that's brilliant. So thanks again, Caroline, for that. So we're just going to set up for the next part, which is get Len to talk about his news item, which also relates to some of what we've seen here tonight. So just I'll mention about these space rocks. There is some books at the back as you come in. It's about meteorites. It's intended for kids, but actually I found them very useful, and I hope you do too. So feel free to pick up one of those books. If you were ever one of those people that wanted to know the difference between a meteorite, a meteoroid, an asteroid, and a meteor, it's all explained in that. And it's intended for kids, but it's actually quite informative, so I'd encourage you to use that. Thanks again, Caroline. And what you might not know is that we do have a small meteorite collection ourselves in the Society. We bought it after our 50th anniversary, when we had borrowed some proper meteorites and moon samples to show at the Castleberry Hub and among other places. So we've got this little collection. Some of them are quite small. And here are just a list of the ones that we've got. So, for example, we do actually have a lunar chondrite and a Martian chondrite. First thing is that, before anyone says, you're not allowed to actually, as an individual person, you're not allowed to own any moon rocks. However, this is actually a lunar meteorite, which is different. It's a fragment of the moon that's come down as a meteorite and fallen to Earth. You're allowed to have those. But there's some interesting ones here. There's some iron ones and so on as well. And the Campo del Cielo one here, a very famous one. And we'll give you a stereo microscope to look at them in more detail, because some of them are quite small. So we'll loan you that if you want to. So if you're interested in meteorites and want to explore a bit more, remember that's a facility that the Society has. So our next meeting is on the 15th of December, and it's our members' images and a bring and buy. So our members' image is self-explanatory. Members submit images and we display a selection of those images, and they talk about how they took them and what's involved in doing them. And also, if you've got excess astronomical equipment, I mean, astronomy can be an expensive hobby, so you tend to upgrade, and once you upgrade, you want to get some money for your old kit. So if you've got any old kit you want to bring along and sell to your colleagues, that'd be ideal. And also you might bag a bargain as well with somebody that's selling something. I've had a few in the past that were very good. So the bring and buy aspect of it, it's we'll set up a table, and if you've got some equipment you want to dispose of, see if you can do a deal with somebody about that. So our members' images, here are just some selection from previous ones. We accept a full range of images. They don't have to be top quality astronomical images. As long as you give it a go, that's what we want to see. So now we're going to do a news item by Len. Now Len is in the distant wilds of south of England. So I'm going to see if I can pass on video control to Len.
Well, this is a new interesting way of doing things. Okay, well, the news is a discovery made by the James Webb Telescope. I'm sure you all recognize the Orion constellation. Firstly, Orion's belt stands out in the middle, and then you have the very bright stars of Betelgeuse, a red giant, and Rigel, a blue-white supergiant. And just below, a little below the belt, is the Orion Nebula, easily seen by the naked eye. And you can see the area of interest taken by the James Webb Telescope. It's quite a small area within that nebula. So let's see if I can get the next slide. There we go. And this is that particular area showing amazing detail. Actually, this picture is a mosaic of 700 images taken by the James Webb over a week of observation. Tucked away in this image are thousands of young stars, ranging from 40 solar masses right down to 0.1 of a solar mass. They've also discovered a number of Jupiter-sized objects free floating in space. On its own, this wouldn't be that unusual, but the unusual part is they exist in pairs. Before I move on from this, let me just talk about the colors in this image. The red in the image is hydrogen, molecular hydrogen, H2. And the green areas are basically organic material, specifically polycyclic aromatic hydrocarbons, or PAHs. They're described as ubiquitous compounds in space produced by stars. And they're basically rings of molecules of matter found, and they're also found in coal deposits, but apparently commonly in space. Aromatic, as I thought, doesn't mean it smells nice. It means the ring formation of the molecules, like benzene. Right, next slide. Oh, there we go. So when they zoomed in on the image, they found 40 pairs of Jupiter-sized planets. You can see each of these pairs blown up here. Ignore the stars, they aren't connected to the object. And the pairs have been named jumbos, or Jupiter mass binary objects. This was a complete surprise, and no one knows how they formed. The last slide. So these are various planetary disks in the image, where a new star is forming as a shockwave goes through the area of gas and dust of sufficient density. Then a star system will start to form. There's two possible ways that a Jupiter-sized object can form. It could be like a very small sun, condensing out of a small amount of gas and dust. However, the physics of this happening doesn't really work in theory. No one has found a way this could happen, but it is still a possibility. Secondly, and more likely, the Jupiter objects formed around a star, and were then ejected from the star system. We know that planets orbiting a star are in a sort of chaotic state, especially at the beginning of a solar system. So the theory goes that if two of those large planets got close to each other, it would have the effect of throwing one out of the new solar system. But it wouldn't throw two out. They certainly wouldn't go in the same direction if two came out. So it does mean that these Jupiter-sized pairs are a significant new find, and no one actually knows how they form. So mysteries are good. I love a mystery. It means there'll be lots more scientists trying to figure it out. And that's the news. Thank you.
So next up, we've got Richard. Richard's going to talk us through what's visible in the night sky.
Okay, so actually it's a really nice, or it was nice evening when we came in. I don't know, very bright moon, Jupiter next to it. Looks really good. Haven't seen anything quite as good as that for some time. So it's always the way. When you have a meeting, the sky is clear. Anyway, now I had a look at Jupiter and Saturn. Saturn is the object down here. You have to, with this stellarium, it gives you everything, and you have to take things away, which is a bit of an unusual way of looking at it. Anyway, right, so this is the sort of setup that you can see this evening. In fact, there was a slight ring around the moon, which is nicely reproduced here. The other night, Wednesday night, I actually went out and had a look at Jupiter and Saturn, and I was quite surprised at how Saturn is now quite a way off opposition, and actually you're beginning to see a gap, real gap with the shadow of the globe on the rings. So Saturn is now disappearing into the twilight, although it's nice to look at, and if you go out early enough in the evening, you can see it reasonably high. But for all practical intents and purposes, it's more or less vanished from the evening sky. Now, if we just come in a little bit closer, maybe, yeah, that's better. See if I can get rid of these star things. These names, don't really need them. Never mind. Okay, so what we're looking at here is the evening sky at the moment. In fact, if you went outside now, this is exactly what you'd see, because this is the time of day. So we've got various constellations here. We've got, this is Taurus, this area here around Aldebaran, and the Pleiades over here. Now, Len was giving a bit of news items a few minutes ago. But the interesting thing is that this cluster of stars that makes up this V shape around Aldebaran, they are a cluster called the Hyades. Now, Aldebaran is a relatively close star. It's a K type star, which means it's orange in color. And it's about 65 light years distant. Now, the Hyades is actually a cluster, an open cluster, but one that we see much more open. And the reason for that is that it's very close. It's roughly twice. Aldebaran is roughly halfway to the Hyades, and the Hyades therefore are not that far away, 120 or so light years distant, which sounds a long way, but in astronomical terms, that's nothing. It's also an old cluster. It contains some yellow stars with a cluster like the Pleiades, which here. Now, if you look at the stars in there, you'll find that they're mostly blue stars. That means that they're giants, they're blue, and they're very hot, and they get through their energy supply very quickly. So they must be young. But whereas what happens with clusters is that as the very hot stars burn off, you're left with stars that are further advanced, and they make up part of that cluster. So with Hyades, it's actually because the blue stars have died off, and you've got the older stars there. it's actually, you've got a few yellow stars as well. And because the reason that it's so big is because it's close. That's the only reason. If it was as far away as the Pleiades, then it would appear just the same sort of size. So the Hyades is what is a cluster that's used for cluster measurements. But recently, astronomers have proposed that there are black holes in the Hyades. Now that's relatively close, and in fact, it's unusual, and it now means that that's about one of the closest areas that we've got that have black holes. So that's an interesting cosmological and astrophysical point, but also that area is very interesting to use a pair of binoculars on, because you can see the different colors. And it's very pretty because you've also got Aldebaran there, which is a bright orange star. So that's, as I say, that V shape makes up the face of the bull. And of course, Aldebaran is the eye of the bull. And his two horns come off here and here. Now, if you've got a telescope and you've got a reasonably dark night, if you go to the star here, which is Zeta Tauri, you'll actually find that there's a little misty object, a little bit up and a little bit to the west, about here. And that is the famous M1, the Crab Nebula. The Crab Nebula is a supernova remnant. The supernova was seen in the year 1054, recorded by Japanese and Chinese astronomers as a guest star. Of course, it didn't occur in 1054. That was when it was seen here. The actual object is about 6,000 light years distant, so it's much further away. So by the time the light got to us, it was 1054. In the 18th century, it was discovered by John Bevis, actually an English astronomer who did a series of star charts of various constellations, and he marked it on. Shortly afterwards, Messier discovered it and gave it the title of M1. Not a motorway, but actually it's interesting sometimes to compare different M numbers with motorways if you really are, that way inclined. Anyway, so it's an interesting object to find, but I have to say that it's not very bright. In fact, dim misty patch sums it up. One of Messier's contemporaries said that it was like the stain of breath on a mirror. And that's about it. It doesn't really have any shape. And it's hard to relate that to the images that you get of these tentacles sticking out. But they were actually observed visually in the 19th century using the big telescope at Burr. The Earl of Ross built a huge 6-foot mirror telescope, which you can go and see, and it is now working with an aluminium mirror. And it did a lot of discoveries in the 19th century of various objects, including things like the spiral nebula or spiral galaxy M51. But he observed this M1. And he called it the Crab Nebula because it looked as though it had tentacles that came out that looked like the appendages on a crab. Actually, we're very lucky because he also looked at another object, an object M97, which is just in the near the plough, which we I'm trying to think what we call it now. It's they called it we call it the Owl Nebula because of the two eyes. He actually said it looked like a monkey. It had the visage of a monkey, so it would have been the Monkey Nebula, but so we call it the Owl. So it's an interesting object to look at and think what's actually going on there, and the horrendous amount of radiation that's coming off of that object. And all you can see is a dim, misty patch. But for something a bit more spectacular, if you sort of plummet this region here, just move your binoculars up and down this area here, you'll come across 3 open clusters that are in almost a straight line. And they are M36, M37, and M38. They're 3 clusters that are really brilliant to look at in a telescope, but sadly, with the way light pollution's gone, they're better seen in binoculars now, which is a pity because you just see little puffballs of patches of light. But M36 is quite a splashy open cluster. M38 is a similar cluster, but it's got a definite cross shape and lots of dimmer stars as well. And the one that's actually in the middle, M38, is a spectacular but rather delicate object of faint misty stars. They make up a pair, and you can sweep between the one backwards and forwards across them with a pair of binoculars, and you can see the difference. So, and also, if you're doing a Messier count, you know, one of these things where you try and see as many Messiers as you can in a given time, it gives you 3 straight away. And if you plan to extend it a little bit over here, you'll come, which is Perseus. This object here is Perseus. This is the Y of Perseus. That's Algol down there, and that's Alpha Persei. And located about here is M34. East around here, you'll come to Gemini, and you've got M35 located here. So there's several open clusters that you can see in the sky, which I'll be coming back to, particularly with Gemini, probably January. So this area here is a rich area of sky to look at. Do have a look and see if you can see any detail on Jupiter. I had a look, as I say, when I had a look at Saturn, I'd look at Jupiter, and the cloud belts are quite distinct, but there didn't seem to be an awful lot of detail. I've looked at a few images taken recently from other places and various magazines, and it seems to be that the cloud belts are quite well defined. But what has happened is that the detail that often is in the equatorial region is much more delicate and fainter. And in a small telescope, it probably doesn't show up very well. It's not particularly any contrast. So it's much more subtle. I can see that there's some detail, but can't actually see it, if that makes sense. I couldn't draw it. So that's another thing. If you have a look, or if you do imaging, it's worthwhile having a look at Jupiter. And also there's a thing that the great red spot is actually seeming to get smaller. I remember when I first observed Jupiter in 1968 with my 6-inch reflector, the great red spot was obvious, and it was red and it was big, but it's sort of disappearing a bit. It's actually sinking down a little bit into the haze that covers the equatorial, the southern temperate zone. So that's about it for this month. But do go out and have a look, and see what you can find. Thanks very much.
Thanks very much, Richard. That's it. Good. Okay.
Right. Okay.
There's something weird going on with that.
Yeah.
So we've pretty much reached the end of our talk tonight. So thanks very much for attending. There's just one thing I want to mention. Jan is helping out with the teas and coffees on a temporary basis because we don't have any regular people, but it's her birthday tonight, so I'd like to wish her happy birthday. So thanks for coming out on your birthday, Jan, and celebrating with us. Brilliant. Thanks again. See you next time.
Yeah.